Hello, everyone, to another week of control systems. I hope you're all doing well. Okay, so where did we stop 2 weeks ago? We were close to finish the system dynamics part, right? So we talked about systems, how we can analyze them in the time domain, and then we moved over to the frequency or the Laplace domain, where we talked about transfer functions. We talked about block diagrams and so on. We figured that poles and zeros are some important stuff for systems because especially poles correspond to the eigenvalues or the solutions of the characteristic equation in the time domain. And they can tell us a lot about if a system is stable or not, right? We stopped when talking about the zeros and we said, okay, zeros don't have much to do with stability. They are mainly there to tell us how the eigenmodes are transferred to the output. So zeros always tell you something about the input-output behavior, how the input is kind of propagated to the output. Okay, so today we got 2 or 3 more slides. Oh, now we got 20 viewers. That's perfect. So everyone's here. That's good. Today I want to actually close the chapter of system dynamics, and then we're going to start with actually controlling. But before that, I figured we're going to do a little bit of a calculation exercise because last semester I figured that students have some problems when transferring the transfer function from one form to the other, and you need to be careful there. So I actually worked out 5 examples which I want to do with you, which should give you the whole picture when I give you a transfer function and then in the different forms, because we have 3 forms of the transfer function. We discussed already 2, and we're going to introduce a third one, but it follows directly from the second one. Okay, that's the thing we're going to start. After that, we're going to finish with the system dynamics, and then we're going to move over in the second part of today's lecture, of today's first lecture, into the what actually control is and how we can do control design and how it makes sense. Okay, so last time I actually basically already showed you this example where we have this transfer function, right? So this is example number 1. We're going to do 5 of those just to get you a full picture on that. So this now is a plain simple transfer function in the polynomial form, right? And we said, so this is a short recap, right? We said, okay, we can transform this in the pole zero form. So how does this pole zero form look like? Instead of 2 polynomials, well, we only have 1 polynomial here. This is constant, right? So it's not that hard. So we only have 1 polynomial. How does the pole zero form look like? Well, we explicitly write the poles and zeros. Okay, so we said, okay, we need to calculate the poles of this function. Well, we know if we calculate the poles 1 and 2, we need to solve this polynomial. We can do this with the midnight formula. We said, okay, -6 plus minus square root of b squared minus 4 times 1 times 5 over 2 times 1, right? And what we get out is, you can solve that, I guess, easily at home. You get out a pole at -5 and a pole at -1. Okay, so we can write the whole system now in the pole zero form. Where is it? Okay, we write the poles. Take care, you need to change sign here as plus 1. So the question is always what goes here, right? And therefore we need to compute the static gain. Remember, the static gain, for example, tells you if you put in a step where your system output goes to in steady state if you just wait long enough, right? So this is what the static gain tells you, because if you there's a question in the chat if we already did that. Well, I started with this form, with the polynomial form, and put it over into the pole zero form. But today I'm going to do a third version. So I thought, because it's two weeks gone, I'm going to recap this exercise for, take these 3 minutes and recap this exercise. But we will build on that, but I want to have everybody on the same page. Okay, so we compute the static gain, G of S, where S goes to 0, right? And this is our K0. If we do so, we get K equal 1, right? So it's 5 over 5. So here's the important thing. Always check the static gain. I need to fix my board for a second because the projection is wrong. Okay. Sorry for that. Okay, now it should work. Okay. Always check the static gain. The static gain should not change, right? Because the step response, no matter in which form you have your system, should always go to the same to the same final value. Okay, so if we put in here G of S going to 0, we would get 5, right? And this needs to be equal 1 because this is what we got here. Okay, so we need to put in a 5 here, right? Okay, 5. I don't know why my ruler is broken today. Okay, whatever. 5. Okay, and now I'm going to introduce another form, which is the so-called time constant form. So instead of poles and zeros, we are actually writing it instead of poles, we are using time constants. Okay, let's compute the time constants of this function. And the time constants, t, they are basically just the negative inverse of our poles, right? So this means 1 over P1, and this is equal 0.2. TP2, 1 over minus 1, the negative 1 is 1. Okay, so time constant form looks like the following: 0.2 times S plus 1 times S plus 1. So again, the question is what goes here? And here's the trick. Because in the time constant forms, you always have ones here, right? They are always 1 because this is the definition of a time constant form. You directly can write your static gain here, and the static gain is 1. So what needs to go here is 1, right? Now, if you check the static gain, it's again 1. So this is, that needs to be the case. So why is it called time constants form? Why is it called time constant form? Well, consider a transfer function, a PD1 transfer function like this. We said here we have the time constant. Right, this is your time constant. And if you Laplace transform this, your G of S gets K over Ts plus 1, right? So this is the form where your time constants directly show up in the Laplace domain. Okay? This is why it's called time constant form. So this was the first example. It's a little bit of an extension of the one we last today because we have this additional time constant form. So why is this important anyway? Why do we have want to have 3 different forms, right? We could say, okay, one is already complicated enough. Well, it really depends, right? What you want to do. We will see, we will design controllers and we will choose the controllers, for example, to cancel poles of our system. And it's simply easier. You get a system from your colleague and said, oh, I modeled this actuator, I modeled this aircraft in that form. It might be in polynomial form, it might be in time constant form, right? So you can choose your controller directly which fits to the form. So without a lot of transformation. But to do so, you need to be able to understand all of the 3 forms, right? Okay. So what's next? I have another 4 examples actually. 3 more, just to get all the different cases we could have. There are always only these 3 forms, but we will see that it can be a little bit more complicated than this. Okay, let's go down a little bit. Okay, so example number 2. And again, we have a polynomial form, transfer function g of s, which is equal for s plus 8 over 2s squared plus 18s plus 36. So what we now have, we have a first order. Okay, let's write it here. This is polynomial form, right? Polynomial form. And we are interested in the pole 0 form and the time constant form. Okay? Let me zoom this in a little bit. Okay. So what we already can say here, we have 1, 0, right? 1, 0, because we have a first order polynomial in a numerator, and we have a second order polynomial in denominator, so it needs to be 2 poles. Okay, let's solve for the poles. Okay, so we need to solve 2s squared plus 18s plus 36 is equal 0, and this gives us our P1 and P2. I'm not going to do this now. You know how to apply the midnight formula. What you get out is P1 is equal minus 6, and P2 is equal minus 3 and minus 6. Okay? Okay, what are the zeros of this transfer function? You need to take the numerator and set it to 0. Okay, let's do this. 2s plus 8 equals 0, and this gives you your 0. And the 0 is equal minus 2. Okay, now we can actually already write the pole 0 form. So, poles and zeros. Okay, what do we have? We have 2 poles. And we have 1, 0 at minus 2. And finally, we need to check this guy here. And we call it just k tilde for. Actually, we're going to use that the whole semester, k tilde, because I introduced that in the summer, in the winter break, just to have it always the same. So we're always going to name that k tilde if it's in the pole 0 form. So my question to you would be now, what's that k tilde? So how big is it? What do I put in here? I give you a couple of minutes, no, not minutes, well, 1 or 2 minutes, and try to think about it. And yeah, what needs to go in there? Remember, you need to compute the static gain, because this should not change. So you can compute the static gain of this g of s. So you let g of s go to 0, and this will give you your static gain k0. So what do we get here? This is 8 over 36, which is nothing but 2 over 9, right? So this is your static gain, and the static gain should not change. So the question now is, what do we need to put in here? Nine? No, not really. We can try. Well, let's see. 2 over 18. 2 over 18. let me think. I think it's much simpler. If you do g of s going to 0, we have k tilde times 2 over 18 is nothing but k tilde over 9, right? And this needs to be equal, k0 needs to be 2 over 9. So k tilde needs to be 2. Yes. So the final answer was right. So 2 over 18 basically is if you let this guy to go s to 0, right? So this is the first step you need to do. Then you get 2 over 18, but this is actually not 2 over 9, right? So you need to multiply this by k tilde to be this guy. So you need to multiply it by 2, okay? Okay, so we put a 2 here. Then it's correct, because then we have 2 times 2 over 18. So it's 4 over 18 is again 2 over 9. Okay. So what do we miss? What are we missing? We miss the time constant form. Okay. So I said, okay, how do we compute the time constants? Well, we compute it for each and every pole in 0, and we just take the negative inverse of the pole. Okay, the negative inverse of minus 3 is 1 over 3. For the second pole, it's going to be 1 over 6. And this time, we also have a 0 here, right? And the time constant for the 0 is going to be 1 over 2. Okay? So, g of s now in time constant form. Let's write it here. Okay, we got it here. Okay. In time constant form. Try to write it a little bit nicer here. Okay, so we've got 1 over 3 s plus 1 times 1 over 6 s plus 1, and we have 1 over 2 s plus 1. So the question now again is, what goes here? So this is already the answer before I raise the questions. Obviously, it needs to go 2 over 9, right? Okay. 2 over 9. And again, because you have only ones here, right? It's always going to be g of s going to 0 is always going to be 1 here if you disregard this guy, because you only have ones here. So you directly can put in your k0 in here. So in the time constant form, your k0 directly shows up here. Because if you let s go to 0, only one ones remains, right? Nur Einsen bleiben übrig here. And this is why this guy is directly your k0. Okay. Hope that's clear. Then we move on. Well, let's see if somebody needs to write it down. Let's put it here. Maybe change the color. For example, number 3. So far, actually, we only had real poles and zeros. So the next question is, what happens when we actually have conjugate complex poles and zeros, right? So we've got 18s plus 36 over s squared plus 4.2s, and we've got plus 9. Okay, we again have 1 0 and 2 poles, right? And we want to know the pole 0 form and the time constant form. Okay, so let's compute the poles first. Again, you know how to do it by now. You need to solve the midnight formula. P1, P2 are, minus 4.2 plus minus square root of 4.2 squared plus 4, it must be 36, not plus but minus, over 2. And now the result here is minus 2.1 plus minus 2.14i. Okay, so we immediately know that this system is going to oscillate because it has a conjugate complex pole pair. So far so good. We said if a system is oscillating, it's often better to compute the poles, not the poles, but the damping and the eigenfrequency. Okay, and the eigenfrequency here is omega 0 is equal 3, which is just the square root of this guy. And the damping coefficient here is must be 2 over 3 to 0.7, right? Because we know that this guy is 2d over omega 0. So we can compare the coefficients. If this was too fast, please look back into one of the first lectures where we discussed the PD2 systems. Okay, so far so good. We also have a 0, right? So let's write down our 0 here. Our 0 is minus 2, so 36 over 18 is minus 2. And the static gain, so if we let S go to 0, the static gain is going to be 4, 36 over 9, right? Okay, so technically we have everything ready to write down the pole 0 form. So now you could go ahead and say, okay, I write down my poles, and my poles are S minus 2.1 plus 2.14i times S minus 2.1 minus 2.14i. And you put the 0 here, S plus 2, and then you compute your K tilde. However, this is not very nice because this guy is complex. This is why we are actually not going to do this. We are not using transfer functions with complex indices. Right? So we don't want to have this I in there. Right? So what else can we do? Well, if you have a second order polynomial, and actually MATLAB and all this software is doing this as well, you simply let your second order system, your second order polynomial, be in that form, right? So don't change it. The only important thing is in the pole 0 form that you have a 1 before the S squared. So this guy is already in pole 0 form, so we can just copy it. S squared plus 4 times 0.2s plus 9. Here, the 0 we can do actually bring in pole 0 pole 0 form, and now we only need to compute this K tilde. And this is going to be a job for you. So how big is K tilde? Anybody has an idea? So nothing has changed, right? The static gain needs to stay the same. It needs to be 4. What do we have here? If you let it go to 0, we have 2 over 9, which is definitely not 4. So if you put G to S to 0, 18, yes, that's correct, right? Because you have 2 times K tilde over 9, and this needs to be 4. So it's 36 over 2, so your K tilde needs to be 18, right? Okay, so again, just to sum that up, if the poles are complex, the pole zero form looks the following. G of S is equal, and you have something here, right? So whatever it is, and the pole zero form is you have S squared plus 2 times omega 0 d times S plus omega 0 squared, right? So the important thing is that you have a 1 here, right? This is the definition of the pole zero form if your system is conjugate complex, right? If your second order pole pair is conjugate complex. Okay, we've got another 18, perfect. Okay, so how does the time constant form look like? Well, the time constant form is similar as when you have real ones. You only put the 1 here, right? So G of S in time constant form. It does not really make sense to actually write the time constant if your system is also oscillating, because they don't have much of a meaning. Okay, the time constant of this guy here, of this 0, is 1 over 2, right? S plus 1. And now the time constant form of this guy, let's write it algebraically. It's 1 over omega 0 squared times S squared plus 2d over omega S plus 1. So you have the 1 here now, right? So you just change the location. And again, because we only have 1s without S, we can directly write K0 here. So in our case, this would look like the following. And now I'm going to scroll up just to get the numbers. Omega 0 is 3 and the damping is 0.7. So it's going to be 1 over 9 times S squared plus 2 times 0.7 over 3, whatever it is, 1.4 over 3, S plus 1. This is going to be 1 over 2S plus 1, and our case 0 was 4, so we immediately write 4 here, right? Done. Okay? So really, if this was too fast, yeah, 4. You can look over it, step by step after the lecture. It's really not that hard, right? It's only important. The only important thing is that you're able to solve second order polynomials with the midnight formula, and then have these 3 forms in mind, and always check the static gain. One last thing though, and this is a pretty short example. The problem with the static gain, namely, is sometimes you have an integrating system, or you have an differentiating system where the static gain is 0 or goes to infinity, right? So then you're not allowed to call it static gain, basically. But let's see, we can use a small trick, and then we also can solve that problem. Okay. So this is going to be the last example now, then we have everything. Example. Okay, could you please repeat how you get omega 0 equals 3? Of course. You have that function here, right? And this is in the form, if you have G of S, let's say we've got 1 over, it doesn't matter what's in the numerator, is S squared plus 4 times S plus 9. So this always corresponds to 1 over s squared plus 2d omega 0 s plus omega 0 squared, right? So if you know that, you immediately know that omega 0 is the square root of 3. So why is that way, right? So why is this case? If you transform that back to the time domain, we know that this is going to be 2d over omega 0 times plus omega 0 squared times y of t. And in this case, we have 1 here, right? Remember the PD2 system, which we introduced? It looked like this. Alternatively, we had the form 1 over squared st plus 2d omega 0 plus, in this case, you need to go this way, right? Let's write u of t here. Isn't it 2 times d omega 0? Yes, exactly. Here it is, let me think. Here it's over, yes, you're right, sorry for that. Got mixed up. Omega 0, and it needs to be, it's too fast, 2d omega 0, right? If you divide it now through omega 0, it's looking like this, yes. And this is why we have, oh yeah, there's an error here. Is it? 2d omega 0 s, yes. So this is not right. This is 2d omega 0, sorry for that. If you now divide this by 3, it's going to be, this by is 2.1, and you divide this by 3, it's going to be 0.7. Yeah, thanks for thanks for taking that closer look. Now it's correct, I think. I was too fast. Yes. These are the two forms, right? And this form gets to that form. And actually, if you have it in time constant form, this is this form. In time constant form, your g of s is 1 over 0 squared s squared plus 2d over omega 0 s plus 1. This is now the time constant form, which corresponds actually to that form in the time domain. I think the lower one is the one we introduced first when we talked about the PD2 system, and then we introduced that, okay, we can simply multiply it by omega 0, and then what we do actually have is here it's 1, sorry for that, and we have omega 0 squared here. So this now is fully correct, right? So there's a close relationship to the form in the time domain, and this is why you can directly compute it from the transfer function. So really follow the path from the time domain ODE your system has, and as soon as you have such a form and you realize it's going to be complex, you can start thinking about damping and eigenfrequency. I hope that answers the question. Thanks for noting that it's 2d omega and not 2d over omega here. Yes. Okay. And here it's correct again, right? Here it's 2d over omega 0. Should be fine now. Okay? So really make you familiar with, as you have seen with me, these sloppy mistakes actually happen pretty fast, and then you have the wrong damping, and you do a simulation and you realize, oh, I screwed up. Yeah, always be careful, careful than me, please. on my paper it was written right, but yeah, copy paste. Okay, one last example. And this time we have a transfer function g of s, which looks the following. We have 3 over s times s plus 10. So what we basically have here, right? So this is the this is actually already in pole zero form, right? Because the polynomial form would look like the following. 3 over s squared plus 10s, right? So this would be the polynomial form. What you realize immediately is that you have one pole at 0 and you have one pole at minus 10, correct? And we don't have any zeros, right? So this is the easy part here. The problem now is, however, that we don't have a case 0, right? So if you let this go to 0, this whole transfer function is going to infinity. And this is actually what happens if you put in a step. This system has a free integrator, right? So it integrates up your input. And if your input is a step, you integrate it up, it goes to infinity, because the area under that step is infinite if you integrate it over time, right? It gets to infinity. However, this is kind of problematic if we want to compare the static gain, because technically there is no static gain, or so to say the static gain is going to infinity. However, you can use a small trick here. You can basically exclude all the free integrator, right? So we can write our system. We can write our system in a way that we exclude this guy, and then we have a PD1 system left, which is 3 over s plus 10. And this guy now would have a case 0 of 3 over 10, right? So now the task is, let's do the time constant form of this guy. If you compute now the time constant, well, the first time constant is the negative inverse, right? So it's T1, it's going to be 1 over 10. And if you do it for the second one, it's going to go to infinite. So there is basically no one. So you leave that guy unchanged here. So you write g of s is equal 1 over, now we can write, let's do it, 1 over s times, and here we're going to write our time constant form 0.1 s plus 1. And now the question is, what goes here? Luckily there's no answer in the chat yet, so you need to think a little bit. Ist es nicht das gleiche, weil k mal 1 durch wieder inf ist? Not sure if I understand the question. No, 3 is not correct. So what do you mean with isn't that the same? So you say I need to put 3 here because it's the same as here? No. What you need to put here, remember, in the time constant form, we immediately can put case 0 and we need to put this guy in here. Maybe that's what you meant with isn't that the same? So you need to put 3 over 10 here. Otherwise, you're changing your gain at when it's approaching 0. But now it's obviously a little bit strange to name that case 0 because there is no static gain. That's why in the lecture we're going to call that case star to kind of indicate that it has something to do with case 0, but it's not really a case 0, but because this transfer function, yeah, has, I mean, you can call it static gain, which is infinite, but yeah, you need to be careful, right? So because it's going to infinite, you could technically say I can put in every number in here what I want, because it's going to go to infinite anyway, because 3 over 0 is infinite and the 100 over 0 is infinite, right? But so that really the S does not need to be exactly 0, but just a very small number, and then this guy has to be correct. So the easiest part is to split that up, consider that as left out, then compute your gain of the PDT n system, and then plug that back in, right? I hope that's clear. So really, if you let g of s go to 0 here, it's going to be 3 over 10, right? And this needs to be the same as here, because this guy is not changing. And still, if you let, for this whole guy, let s go to 0, it's going to get to infinite. But it will go to infinity no matter what you put in here, right? So that's the problem. That's why you cannot just take the same thing. Okay, that's basically it, and it actually took me longer than I was thinking, namely about 45 minutes, but it doesn't matter, because this stuff is really important, and I figured that a lot of students fall over that issue when they get a transfer function in the exam, and then start to out of any reason start to transform from one form to the other. Usually you don't need to do it, but you need to know that there are 3 forms, because you need to select your controller, right? When you select your controller, it's also going to be a transfer function. And if the system is in pole 0 form, it often makes sense simply to select the controller in pole 0 form, because then you can start canceling things. And this is actually what it brings us to the next, or the final idea of the system dynamics part, namely when we are allowed to cancel poles and zeros. Okay, and here I'm gonna actually start with this one. What do I mean with pole zero cancellations? Let's say you have a system G of S, and it looks the following, right? You transform your system and you have something S plus 2, and you might have, I don't know, 10 here, and S plus 100, and S plus 440, doesn't matter, and S plus 1. Okay, right? So this is, okay, this is a nice transfer function. We know it has 3 poles, it has 2 zeros. We can compute the stability. This guy is going to be stable because it has poles only on the left-hand side. All the zeros are on the left-hand side in our pole zero map. So, good, right? But if you take a closer look, you see that you actually can simplify that system, right? You can cancel that out. Okay? You can simply do this because this is a rational function. And let's say you have make it even simpler. You say you have a system S plus 1 over S plus 1. This is obviously 1. You easily can cancel. Everybody, I'm quite sure of you, sees that. However, transform that back in the time domain. You would have y dot plus y is equal u dot plus u, right? And you would not think about canceling anything here, right? Here it would be an ODE and you would try to start to solve it. But in reality, if you transformed it, you would see, okay, the solution is pretty simple. My transfer function is actually just 1, right? So this is a very big advantage of the Laplace domain, that we can simplify our systems by just canceling things out, right? While in the time domain, at least I would not have seen that I'm allowed to cancel here in the input-output behavior, right? Based on that ODE. So the question now is, when does that appear? How does it appear? And maybe we can make use of that, right? Okay, and this finally brings us to the last the last things we have in the system dynamics part, namely pole zero cancellations, right? So I always told you the poles we have in the Laplace domain are the same as the eigenvalues or the solutions of the characteristic equation in the time domain. However, this is only true when we don't cancel our transfer function, right? So what is this canceling about? If we cancel a pole with a zero, then it does not occur in the input-output behavior anymore, right? So what we actually do, we take that eigenmotion, right? Remember what an eigenmotion is. It's how your system behaves, right? This guy is oscillating, so it has a conjugate pole pair. If we cancel that out, it does not behave that anymore. But you could say, okay, but this guy still does that, right? That's true. However, you cancel it with your zeros. So it does not show up. So you found basically, what you did is you found an input where you don't excite this eigenmode. Very simply said, think of a car and you're driving, constant speed, and you are basically want to know how is the eigenmode with accelerating and deacceleration, right? You would simply take the gas pedal, right, and change the speed and see how is the car behaving. Now, if you take the steering wheel, well, your speed will not change that much. Obviously, if you do this, it will change much, but let's say you do it with small. So from an input-output behavior, you're not influencing the speed with your steering wheel in a perfect word, right? And then technically you would cancel that out. This is actually exactly what a pole zero cancellation is doing. You're canceling the eigenmode of in the output behavior. So your eigenmotion does not show up in your measurement anymore. Okay. And why is this important? Because as engineers, we are primarily interested in that input-output behavior. So we easily can cancel this. So let's consider this. It's a PD2 T3 system. We've got 3 poles. We've got 2 zeros. I mean, we can work with this guy, right? But we know it's a little bit complicated. But now let's assume this first zero here is equal the second pole, and the second zero is equal the third pole. Okay, now we can cancel, and now we still only have a PD1 system. And working with this PD1 system, it's much easier than with this PD2 T3 system, right? So that's the idea, right? That's the idea. What, however, when are we allowed to cancel? Or the next thing is, when should we cancel, right? So I give you a PD2 T3 system and you simply cancel, fair enough. You got a much simpler system. You say, okay, the eigenmodes they are stable, hopefully, and they fade out anyway, so I'm canceling it out because I can, right? It's just a mathematical rational function. When should you not cancel, right? There's always a but in control, I told you. When should you not cancel? You should not cancel if your pole is in the right half plane. Okay, I try to explain what I mean with. If this is your pole zero map, and you have a transfer function s plus 1 over s plus 1, your pole zero map looks the following, right? You have a pole here, and you have a 0 here, and you simply cancel it out, it gets 1. This is okay. However, never ever, and this is really important, never ever cancel a pole and 0 on the left half plane. Right? Why? There's a simple explanation why you should not do this, why you're not allowed to do this. And actually MATLAB, I think, doesn't do it either when you have an unstable pole. Okay. On the left-hand side, I mean, the pole, the eigen behavior is still there in your system, right? it just doesn't show up in the output behavior. And in reality, you will not, this is a linear model, right? It's going to be an approximation of your real world. In the real world, you might have a measurement which still measures that eigenmode a little bit. However, you say, I don't care because it's a stable one. It's on the left half plane. So this eigenmode, remember, it decays exponentially. It goes to 0. It does not show up. Okay. However, if this eigenmode is unstable, it goes to infinity. And if you're off just by a small percentage when canceling it, right, then this eigenmode will show up and it goes to infinity. Okay, so bottom line, never ever do a cancellation in the right half plane here. I will have a MATLAB example in a second. Why you should not do it? These are the explanation. Because you will have an unstable system. As I said, we are working with linear system. All these PD2, PD1 system, they are an approximation of our real world. In reality, our system is a little bit more complicated than this. It's an approximation, right? And when we cancel a pole with a 0, because our transfer function tells us, we are canceling something, but the pole and the 0 might not be actually there where they are in our model because we approximated our aircraft with a linear model. But that doesn't matter as long as it is stable, because if your eigenmode is stable, it goes to 0 anyway. You don't care. But if your eigenmode is unstable, it will go to infinity and it will dominate your output. And so you're working with a fully different system when you cancel something on the right-hand side. Okay. Okay, so let's try to come up with the MATLAB example here. Okay, it's always good. Okay, so I need to do it by hand. I think it's gonna be this one. Yeah. Okay, so I show you a practical example. What we do have is a PDT3 system, and it has a 0. Also, here's the English one. You can read it in German as well, if you like. We have 3 poles here, and we have this 1 0, right? And you see that this guy here is exactly, this 0 here is exactly that pole here, right? So if you take a look at the pole 0 map, it's directly over each other. So now you could say, okay, this system here is a little bit complicated. I'm going to cancel these 2 guys. So my simpler system is simply a PT2 system, right? With 1 pole at -3 and the other one at -1. Okay. And you see the 2 systems are behaving exactly the same, right? Because the transfer function are the same, right? Because it gets cancelled out, this eigenmode. It's perfectly cancelled. So the 2 systems, if I excite them with a step, they need to look the same, no error, because it's a perfect cancellation. So the red one, by the way, is the error. Okay. So now let's assume the cancellation in reality is not exact, right? So now let's assume this 0 here in reality is just a little bit off that pole, right? So we have a pole at -2 and we have a 0 at -2.05, right? Okay. Now you say, okay, I still want to use my simplified model, which is this one, because I don't care that this 0 is a little bit off. Okay, let's compare the 2 systems. So the blue one is the system which we cancelled, right? This PT2 system. And the green one now is the actual system, this one here. And obviously you see there's a small difference, but it's very small, right? It's probably a couple of %. And this will always be the case. When you do cancellations, you will never have this exact cancellation in reality, because your linear system is just an approximation of reality. If I give you in the exam and I say, okay, this aircraft is a PD2 system, it's definitely not going to be PD2 system if it flies in the air. There will be nonlinearities, right? Which we are not considering. It's just a simplification. This might happen. So now let's see what happens if we do the same thing in a right half plane, right? So this is fine. I mean, we as engineers like to work with approximations, and we don't care that this is a couple of percentage off. So now let's consider what happens if you have a system and you have a pole at +2, so an unstable one, and you have a 0 at +2. Okay, so your pole 0 cancellation now appears here. So, okay, let's say this guy here is our approximated system, right? We don't care that it's on the right hand side. We simply cancel that out. Chuck, chuck. What remains is the same PD2 system. Okay, if you now simulate it, it still looks the same, right? Because it's the same thing as before. The cancellation happens on the right hand side, but we are assuming we are hitting the cancellation exactly. Okay, but now let's assume, okay, it's not fully exactly, right? So let's assume our 0 here is 0.05 off. And remember what happened in the stable case. We said we can live with that, right? This is a couple of percent off. We still can work with the green model, and we just need to make sure that our controller might be robust. And now, if you do the simulation with this a little bit off, you see the following. The green one is the system we work with, and the blue one is the actual behavior in reality. And I hope you agree that these two things are not the same anymore. And even wenn man alle Zehennägel, wenn man alle Hühneraugen zudrückt, this is not going to be the same, right? Don't cancel on the right half plane, please, because it will always go wrong. Okay, so I hope I could convince you that you should not cancel on the right half in the right half plane. Last but not least, the question: when does a pole 0 cancellation actually appear? I've shown you what a pole 0 cancellation is, right? Technically or mathematically, it's pretty simple. You have a pole and you have a 0 on the same location, you cancel it. You're allowed to do that in the Laplace domain because we have a rational function. The question now is, why does it actually show up, right? So when does it actually happen? Well, first thing is, a cancellation results when you model your system, simply due to the characteristic of your system. And I think you can read books about poles and zeros, right? And also about cancellations. For me, always the most simple example is when does a pole 0 cancellation occur is, think of a rope, which you know that game where you go up with the rope fast, where you see the eigenmodes of the system. Okay, let me try to paint that. So let's say you take a rope and you move that pretty fast up and down. So it will show, the rope will go like this, right? Up and down. So when Seilspringen quasi. The rope will kind of make that wave. Okay, this is an eigenmode actually of the rope. So if you place a sensor in that rope here, you will measure this displacement here. That's fine. You will measure the eigenmode. Now place the sensor here and you will measure no displacement, right? So although the rope is moving up and down, you place the sensor in a location where you don't see any movement. And this is actually what happens when you have a pole 0 cancellation. The eigenmode of your system is not showing up in your sensor signal. So you can think of, instead of a rope, think of an aircraft wing, right? That's actually a pretty interesting research topic today, because we are building now aircraft of carbon fiber. What happens is that these wings get don't break it, get very elastic, right? So, and also that wing has this kind of eigenmodes our rope has. So this wing, a little bit accelerating, goes up and down like this. And if you place the sensor on the wrong location, you will not be able to measure that movement, right? And this is actually when a pole zero cancellation in a linear sense appears. Okay, so it's a modeling problem, right? This is the first thing. The other thing is when you actually have a desired pole zero cancellation. That actually brings us now to the idea of control system. Let's say our espresso machine has a pole which is pretty slow, a time constant which is pretty slow, so a pole at -10, and we have a pretty fast one, something like this. Could be an espresso machine, could be anything you like, okay? And now you're saying, okay, what I've learned now so far is that this eigenmode kind of dominates my response. So my response of that system will take some time. It will need over, sorry. Yeah, it will take 0.1 seconds times 3 to reach 95%. The other one with 0.01 second, this is pretty fast. This disappears pretty fast, right? So my system is dominated by this 0.1 second eigenmode. This guy is the reason why my espresso machine needs so long to heat up. So what you can do is say, okay, I design a controller now. I'm applying an artificial system which kind of looks like this. And you're going to take out this slow response of your system. And this is actually the idea of, or one of the first ideas we're going to do in controls. We're going to design controllers based on pole zero cancellation, where we say, okay, we got very slow eigendynamics. We're going to cancel them out to make our espresso machine, our aircraft, our car faster. And this is actually a pretty common technique, especially in process control, because you can accelerate your system with a very simple idea, pole zero cancellation. Okay. However, don't be scared. We're going to discuss this in more detail, but this is the turnover, so to say, to the idea of control systems. This is going to be the next part. Okay. So that's it for the system dynamics. We've got 25 minutes left, and we're going to kick off the control system topic in a second. So we've discussed about how systems can look like, and really what we've done so far is we've discussed the characteristics and the possibility for us to analyze physical system. You have a physical system, you have an espresso machine, a car, an aircraft, you do the modeling, right? You come up with ODEs as you've learned in your other subject, and now you're able to have a unified toolbox, so to say, to analyze these systems, right? You can do step responses in the Laplace domain pretty fast. You can look at the poles and zeros and analyze these systems. This is where we are. But now we want to modify this system. We want to make the system behave in a way that we like it as engineers, right? So we want to change that dynamics. As I said, we don't like that our espresso machine takes 10 minutes to heat up. Either change the hardware, well, we can do that, but yeah, it's not a part of control. This is more the hardware design, or we can artificially change it, right? This is the idea of control. Okay, and this is going to be the next part. So, introduction to control systems. And the good news is also our control system will be most of the time be a transfer function and look linearly, right? But we will get to that. Okay, again, let's have an update where we actually are. this is a control loop, right? I think I've shown you that guy in the first lecture, where we have our plant. So this is the hardware, our physical system. Can be your car, can be your aircraft, whatever your area you're working in. We have some measurements, and we take the measurements and feed that back to and compare it to the reference. If this is your espresso machine, you measure a temperature and you compare it to a desired temperature. And the control arrow gets into the controller, and the controller creates a control input, as you have done hopefully with the espresso machine. So you should know what a control loop is, right, by now. Okay, so far in the lecture we mainly dealt with this guy here. We dealt with how can we analyze the system, how can we get the characteristics of the system, how does it behave. As soon as we know how it behaves, we now can change this behavior. Why do we want to change that behavior? Well, think back of the very first lecture, the motivation of control. A rocket needs to be stabilized, right? If you have just a rocket without controller, it will fall down. The espresso machine, you don't want to tell the user how much watt or power input he needs to put in. It should be convenient to the user. He should be able to select a temperature, 96 degrees, for example, right? You need a controller which takes your desired temperature and computes the power by itself. So we want to make the system behave as we want. We basically want to make the system a little bit more intelligent. Okay, this is why the next part mainly deals with this guy. With this guy. Right? How to design a controller. Okay, so the thing is, and this is also relates back to the very first lecture, nowadays controllers are fully digital, right? So what does that mean? We basically have a computer program. A controller is a computer program, and the problem with this computer program is, how does the computer program control our car or our aircraft or whatever, our robot, right? Well, we need to put that computer program on a microchip, like this guy, or on a SPS or whatever you like, and then it gets connected. But we need something to kind of measure a variable and kind of take the command from our controller and bring it back into the physical world. So we need sensors and actuators. I know you have own lectures for that, so I'm not going to go into much of a detail about sensors and actuators. For us, sensors and actuators are simply a piece of hardware, and they belong to the plant, right? So, practical example, your aircraft. So the system itself is your aircraft. You have an angle of attack measurement, you have a speed measurement, you have a pitot tube. These are your sensors. And as actuators, you have hydraulic cylinders, which steer your elevator, your aileron, your rudder, and so on. Your engines, they are all actuators. From a control perspective, we all going to stick that into the plant, into the system, right? But obviously, as a control engineer, you always have to be sure, or you have to make sure that the actuator and the sensor is there, because you cannot control the espresso machine when you don't know the temperature. So you need to measure the temperature, right? Okay. So we're going to stick those things all in the hardware. I know this might sound trivial, but usually what always happens if somebody starts working on a project in control, oh, I have this system, I'm designing a controller, and then the question comes, okay, do you actually have the right actuator to make that work? Do you have the right sensors? So from a control perspective, you need to make sure that it's going to be there and it's going to be working correctly, right? So otherwise it's going to go wrong. Okay. So the question now is, how does such a controller look like, for example, mathematically? Well, since we have discussed mainly linear systems, right? We said our system here, G of S, is linear, our aircraft, our electric circuit, and so on. It kind of makes sense to also consider this controller here. Controller C or R for regulator, whatever you want, as a linear system, right? So it's just applying all the things we know, right? This is why in this lecture we're not gonna start with that, but mostly we say our controller is also gonna be a linear system. Most likely it's gonna be a simple transfer function, right? And the job for you as control engineer simply is you need to select how should this controller look like in the terms of a transfer function, because now you have all freedom, right? If I give you a system, this is going to be a transfer function, but this is going to be set. This transfer function depends on the hardware. We model it, we get a transfer function out. For the controller, you are completely free to choose any transfer function you like. The question is how, and this is what we're going to learn in controller, right? Because we are now only dealing with linear system, we're going to say now our controller is also going to be linear. And why is this a good idea? Well, because there are a lot of good mathematical tools which work pretty well in linear. For example, in linear system. For example, this poles and zeros, right? You look at your transfer function, you immediately know if your system is stable or not by looking at the poles. If your system is not linear, there are no poles and zeros anymore, right? So this whole mathematical view breaks down when your system is not linear. So it makes sense to talk about linear controllers. And I would say 95% of the controllers around are linear, are PID controllers. You might have heard that sense. So for us here in the lecture, we can say, okay, we can apply simply the tools we've learned by considering linear controllers. Okay. And this is now my own very rough categorization of different controllers. We consider linear controllers, they're going to be our primary topic, and all nonlinear effects, we're going to talk about that later, right? What are nonlinear effects? Well, think of the aircraft. There is a maximum rudder position you can go. This is a hard nonlinearity. Everybody knows hard nonlinearities. If you drive your car, there's a maximum position you can go your steering wheel to. There's a maximum position of your gas pedal position. If you consider a robot arm, there's a maximum position he can go down, he can go up. These are all nonlinearities. If you have a linear system, they don't play a role there. So we're going to approximate our real world with a linear system, and we're going to talk these constraints, these restrictions later on. Obviously, there's also like a broad field of nonlinear controllers, right? For example, 2 or 3 point controllers. And actually, why is it red here? It's red here because we're going to start out with that controller. And let me fix the typo immediately. Otherwise, I forget it. It's so-called bang-bang controller. And I'm pretty sure every one of you is using such a bang-bang controller on a daily basis. Well, this is a pretty simple one. Then we have sliding mode controllers, adaptive controllers, nonlinear dynamic inversion controllers. So on each of these topics, you can do a PhD basically on it, right? So we're going to stick to the linear world. The only exception is we're going to talk about a nonlinear controller, the so-called bang-bang controller, in a minute. Why? Because it's simply often used. Again, please really be aware of the fact that a linear system and a linear controller, or mainly a linear system description, is an approximation of the real world, right? So technically, what we're going to do is we're going to design a linear controller for a linear system. But in reality, you're going to take that linear controller and plug it onto your hardware, your espresso machine. And this system is going to be nonlinear. It's not going to be fully linear. This is really just an approximation. I know I kind of repeating myself, but this is important because what often happens is, oh, I have this nice controller for that model, but it does not work in practice. Why? Because your actual world is nonlinear. So there is this additional step you always have to take. Okay, so let's talk about this bang bang controller. And it's actually really, really simple. You will see that. It basically, or let's start differently. What is a linear controller doing? A linear controller takes your control error and computes an input, right? So if let's say your controller is simply 1, it takes an error of 5 and multiplies it by 1, and your output is going to be 5. If your control error is going to be 10, the controller is 1, the output is going to be 10. So you have basically a continuous adaptation of the output depending on your control error. You have an infinite number of control outputs, right? Think of a speed control of a car. Depending on the error, your engine gets a command how much rotor speed it should drive, right? Or should have, right? And this can be 100, 101, 2000, whatever. So this is going to be a continuous space where your control variable can be. A bang bang controller is much simpler. It only has 2 states. So independence of your control error, your nonlinear bang bang controller only has 2 states, and most of the time it's going to be on and off. Well, obviously there's an extension when you have, I said to you, it's like 2 or 3 point controller. The bang bang controller is a 2-point controller. The 3-point controller is a natural extension basically of this bang bang controller. It can simply have fully on, fully off, or fully on into the negative direction. For example, let's say you want a temperature control, you can go full heating, full cooling, or just do nothing. That would be a 3-point controller, right? A lot of times you only have on and off, especially you will see the examples there. They are actually pretty simple. Okay, so if you want to draw a diagram of your control command over the control error, so the simplest way to do so is simply you say my control error E, and then I have a control command which is basically 0 command and on and off, right? So this is going to be off and this is going to be on. So when the control error is just small enough, it's off, and if the control error gets too big, it's going to turn on. This effect again, it's going to turn on, right? So this is the most simple bang bang controller, right? So if my control error is small, E is small, we're going to turn off, and if E is big, we're going to turn on, right? So what's the problem with that? Well, the problem with that is that if you say a classical bang bang controller is your oven, right? If you want to heat up your oven at 200 degrees, you switch it on. The sensor says, okay, we have 20 degrees and we want to reach 200. Okay, let's go full power, switch the heater on. You reach 200 degrees, in this case, you would switch it off, right? Maybe the temperature increases still to 202, 203, but then goes down to 200. And then you're at 199, and suddenly we have a drop in temperature. And brauchst du was? Sorry for that. Johannes? Brauchst du was? Ich bin nur in der Vorlesung. Nee, der ist heute nicht auftaucht.
Aber so lose Termin vereinbart hatten.
Nee, er hat heute auch Vorlesungen, er ist nur in der Früh nicht gekommen.
Der hat gesagt 13 Uhr bis 13:30 Uhr. Kann sein, aber er ist schon hier. Oder?
Nee, ich habe ihn nicht gesehen heute. Also ja.
Dann hat er vielleicht gemeint per Zoom oder was?
Ja. Okay. Oh, sorry for that. Professor Minslav was here to check for Professor Westenthaler, but nobody showed up here. Maybe the weather is too bad. So, okay, back to the example with your oven. Where were I? Okay, the problem is you switch the oven off at 200 degrees. It falls to 299, you switch it on again. It reaches 200, you switch it off again, right? So there's a lot of switching, and this switching will kind of make your hardware not very good, right? So it's kind of will degrade your hardware over time. And this is why we're going to use a hysteresis, right? And this is what this figure is about. So instead of what I've shown you here, having one single switching point, you have two switching points. So consider that example with the oven. You want to reach 200 degrees. Okay, you start here at 20 degrees room temperature. Now we're going to start from here. 20 degrees room temperature. So we got an error of, if we got 20 degrees, we got an error of minus 180. Well, it's a little bit the wrong direction, right? So it's not a good example. Okay, but you know what I mean. We have a control error of 180 degrees. We switch it on. And when we reach, let's say, a control error of 20, we switch it off. And here, minus 20, we switch it on again. So that means, technically, we heat the oven up until 220 degrees. We switch the controller switches the heater off, and it waits until it goes down to 180, and then we're switching on again. So we are basically moving between 220 and 180. Well, for an oven, maybe a delta of 40 degrees is a little bit much, right? I just want to accelerate this example a little bit to show you what it means. Obviously, you will probably choose a value of 195 and 205 degrees. So your control error can be plus minus 5 degrees, right? The point is, if you make that too small, you will be better. You will reach the 200 degrees better, but there will be a lot of switching. And this is the job for you as an engineer then to select the right switching points, right? It's a matter of how hard should I go with my hardware? Can I go with a lot of switching, or will the oven be broken in like 5 months when I switched it often? So I better put in better hardware, or I increase the hysteresis. Right? So these are the possibilities you have when designing a bang controller, and only those, right? Again, simple examples for that: a stove, a boiler, right? Boilers as we have here at the Hochschule. I know you have not been here for some time, but if you go to the toilet, you also sometimes you have boilers there. They are basically have this bang controller, right? They try to keep the temperature within these hysteresis windows of probably, I don't know, 40 to 50 degrees or whatever you select, right? So very simple controllers, but good thing they are pretty cheap. So if you want to draw the control loop, you have your system, you have a measurement, you still need to measure something, and depending on your control error, you only have these two states. You have basically on and you have off, right? What you can select is obviously this on and off. So how much goes in and goes out. So what does on and off actually means? Does off mean really zero, or does it just mean lower and more heating, for example? And you obviously need to select those switching points here, right? Yeah. Again, this hysteresis is there. You prevent too many switches because this is putting some load on your component. And if you have higher hysteresis, you have fewer switching, but you have greater overshoot. So I will show you that in a second in an example. In a practical MATLAB example, what that actually means. Okay, so if you consider this PD1, this is just an example, right? This is a PD1 system. You have a time constant in 2 seconds. And my input is here. I want to have a reference of 1.5. So I put in here 1.5. This is the command I want to get to. And you see my variable, my output. So the red one is the system output. For example, the temperature is oscillating around that 1.5. This is the drawback of the bang bang controller. It's really hard to hit your final value you want to achieve, right? Obviously, you can make the hysteresis smaller, then you will have more switching and you will get closer to that 1.5. On the right hand side, you simply see the control input, right? You see either it's 0 or 3, which 3 means on, 0 means off. And the green one is basically the control error. So the control error is always going up, down, up, down. Yeah. Okay, but now let's see the MATLAB examples. Again, not possible. I don't know what's going on here. Where is my MATLAB? Here. So here's this PD1 system. Let's make it a little bit bigger. Okay. Here's this PD1 system, and you actually have this bang bang controller as a built-in block. What goes into my system is a step input at 1.5. And here I've set this, it's the same example as in on the lecture slide with a switch point of 0.2. So the hysteresis is plus minus 0.2. And the output is 3 when it's on and 0 when it's off. So if you do the simulation, you will see that you get this, right? So this is now the answer. I want to reach 1.5, but I'm oscillating around that because I'm only switching on and off. Okay. The lower example now has the following. It has a very small hysteresis. So as soon as I'm 1 over 1,000 above or below my 1.5, I'm going to switch. And what you will see is it now follows perfectly, right? So I'm reaching my 1.5 perfectly, but you see the switching here. If you zoom in, or not, if you zoom in here, you see that there are a lot of switches. We are basically switching, I don't know, 100 times, no, even more per second. If you zoom in here, you will also see the switching points, right? So we get a much better result here, but we have a lot of more switches. So this is the thing you as an engineer need to decide when you design a bang bang controller, right? To be fair, that's all we have in the lecture for the bang bang controller. There are some pros, some cons, which I'm going to try to summarize. So the pros are really, it's simple, and you actually don't need, often you don't need a microcontroller. You can do an analog implementation. You only have a few parameters to set, and it's often sufficient for different applications, like your oven at home, a boiler, right? These are pretty simple. You don't need to have a fancy microcontroller. Obviously, if you want to build a high-end oven, like if you buy, I don't want to do any advertisement, but I'm quite sure that, I don't know, a Miele, for example, has a little bit a more sophisticated controller in there. Okay, the cons. Well, you usually don't have good reference tracking because you need the hysteresis, because you're going to destroy your system pretty fast if you don't go with any hysteresis. But you can have good reference tracking, but it will have a very high component load. The system is unfortunately not non-linear, right? So what does that mean here? It will behave different for different inputs. A linear system, if I go in with a value of 5 and my output is 10, I know if I go in with 10, my output's going to be 20. So there's a linear dependency. While for a nonlinear system like this bang bang controller, I don't have this dependency. So it's really hard to work with this system if you do have very hard constraints in your design. Yeah. So basically what I'm trying to say, it's unsuitable for a complex control task. So that's why if you have a complex control task, you want to go with linear controllers where basically for each control error, you have a different control input. If this was too abstract, simply said, you don't want to have an automated driving car with a bang-bang controller. Think of it, what that would mean. If you want to keep the middle of the track and you only have full left, full right, or nothing, right? Everybody knows this is not going to work properly because you will crash your car immediately. A bang-bang controller for this situation is not a good idea. Your aircraft, your autopilot for holding the altitude, right? If you have a control system which only can do this, this, and this, it's probably not going to work. You really need a smooth behavior of your aircraft. This is where linear controllers come into play. If you want to build a cheap oven, a cheap espresso machine to hold the temperature, a bang-bang controller can do it. So this is really a design decision. And how much money do I have? How much money should my product cost, right? And all this goes into it when you design for a bang-bang controller or not. Okay, see you later.